getting started, remembering to press the button here. Well, okay, press a different button there. Going to start off with a problem for you to do based on part of what we had in our lecture and lab yesterday. So this is a clicker question. A hydraulic lift has a hydraulic ram cylinder with a cross-sectional area of 2.50 meters squared. What pressure must a hydraulic pump provide to pick up a 30,000 Newton pickup? Okay, still missing Gila, Abby, Michaela, Edward. Those three. Gila, you're up. So, Abby and Michaela. Okay, everybody has answered. Our answers were, hey, look, pen failed again. Pen should be arriving today or tomorrow at the latest, along with the keyboard, so I can do things like paste, copy, all those kinds of nifty things. Okay, so we have two people who said 7,500 pascals. That's a 2. 0 that said 30,000 pascals. 18 that said 120,000 pascals. 3 that said it depends on the cross-sectional area, and only you can tell me how many answered the last one. Because yeah, it's not showing on my screen. Okay, let's we have a pretty clear distinction, so I'm going to go straight to Arlene. Explain how you got your answer. Well, first tell us which one you got. Okay, Arlene got C by simply taking force over area. Pressure is equal to the force divided by the area. And so the force that was being held up was 30,000 newtons, and the area was 0.250 meters squared. And of course, we probably are all astute enough to know that 0.25 is 1/4. So if you divide by 1/4, it's the same as multiplying by 4. 3 times 4 is 12. Here's what happens when I get a phone call, in case you're curious. That's how I know. Okay, so the answer was exactly what Arlene said. Good job. Better make sure I mark down a score for her. Any questions about that answer? There were 2 people who said 7,500. How would you get 7,500? Yeah, you divide by 4 instead of dividing by 0.25. Or as Gila said, you multiplied by the 0.25. So that was the wrong units. That's an example of where units can help you out. Meters squared times newtons is not a pascal. Pascal is a newton per meter squared. And 3 people said that it depends on the cross-sectional area of the hydraulic pump. It only, because we're looking at the side that's lifting the car and we know the pressure, it doesn't matter what's going on at the pump. It just matters what the pressure is. So the pump doesn't matter as long as it can reach the pressure that we need. And the cross-sectional area of the pickup is not what the liquid is hitting. So that's why that one would make no sense. Okay, a problem for you. Actually, on my desktop, you probably see I have a picture of the Maltese Falcon as an example of this, because the Maltese Falcon, of course, is what this is based on, a gold statue of the shape of a falcon, has a weight of 24.1 newtons. By this point, hopefully you're familiar with the newton as the unit of weight. We would measure things in pounds, and some people would say kilograms, but what are kilograms actually measuring? They're measuring mass. I'm probably going to rewrite the experiment we did yesterday and just not have the recalibrating it in grams, because a lot of people seem to have confusion on the units based on that. So we have this statue that is purportedly 24.1 newtons of gold. And we have here the density of gold. What was the density of mercury? Do you remember from yesterday afternoon? 13.6 grams per centimeter cubed. So gold is significantly more dense than mercury, which is more dense than lead. So it's pretty dense material. You know that somebody's not going to put in something more dense than gold in their gold. Okay, so we want to check this. So we're just like Archimedes, given a task of don't destroy the golden falcon, but determine if it's really pure gold. And so knowing about Archimedes' experiment, Archimedes' principle, and what we did in lab yesterday, when the statue is completely submerged in a container of water, the weight of the water that spills over the top of the bucket is 1.25 newtons. What important information do you get from the weight of the water that spilled over the bucket? Okay, that's the volume displaced. Well, it's the weight of the displaced fluid. So we can determine the volume displaced from this number. Why doesn't it tell us the buoyant force? Well, it does tell us the buoyant force, actually. But yeah, it tells us the buoyant force because the weight of the fluid displaced is equal to the buoyant force. So my question was a different one, and I will just retract my question rather than trying to state what it was. The buoyant force is equal to 1.25 newtons, because that's the weight that was displaced. The buoyant force is equal to the weight displaced. That is Archimedes' principle. So we have this relationship, and then it says find the density and specific gravity of the metal. Is the density consistent with the claim that the falcon is solid gold? So how do I find the density of my statue based on this information? And we can go back to what James said because it was leading us in the right direction. How do I determine the density? Density is equal to blank over blank. The mass over the volume. So if it completely sinks, because you know gold is going to completely sink in water. Gold is more dense than water. What's the density of water? 1 gram per centimeter cubed. So the gold definitely sinks. Hence, the volume displaced, we know immediately the force buoyant is equal to the density of the fluid times the volume displaced times G. Therefore, the volume displaced is equal to the force buoyant over density of the fluid times G. So I know the volume displaced based on the number they gave me. Now I also need to know the mass to get the density. How can I find the mass? Do what? Okay, from the force, we know the force of gravity is equal to mg, and we have the force of gravity right there. So that means the mass is equal to the force of gravity over g. So let's put these two things into the equation for density. That color. And notice my G's now are going to cancel. Force gravity over G, force buoyant over real fluid G. The over G's cancel. So the density of my material, the gold, is the density of my fluid times the force of gravity divided by 24.1 divided by the buoyant force. And so, of course, you don't need to put 1 into your calculator. That's just 24.1 divided by 1.25 is equal to 19.28 grams per centimeter cubed. How many significant digits do I have? 3. So the correct answer is 19.3 grams per centimeter cubed. That's the density. Is that going to match with the gold? I have 3 sig figs to 3 sig figs. They're exactly the same. I'm going with this pure gold. What's the specific gravity? Do you remember how to do that? Well, fortunately, it's the simplest thing in the world. Specific gravity is equal to the density divided by the density of water. It's equal to 19.3 grams per centimeter cubed divided by 1 gram per centimeter cubed. What does that division really do? It just drops the units. So specific gravity is 19.3. So specific gravity, it implies a certain unit, but it drops units. It's a unitless quantity. Why does it imply a certain unit then? Well, because it's divided by the density of water. And so it's going to be that number times the density of water in whatever units you like. So that turns out that was a pretty easy calculation, and it's a calculation you did over and over. Well, over and over, probably 3-4 times yesterday in lab. Gila.
Is it the density of water or the density of fluid that
It's divided by the density of water. This is, let me change the color of what I circle with. For specific gravity, it's always divided by the density of water. And in fact, it's divided by the density of water at 3.98 degrees Celsius because that's the density that is exactly 1 gram per centimeter cubed. Or that's the temperature when the density is exactly 1 gram per centimeter cubed. Okay, now, before I move on, because I'm going to be moving on to capillarity and whatnot, I want to first talk about suction cups. Currently, in my shower, I have a couple things held up by suction cups. And one of them, I say currently because I'm afraid it's going to fall. The suction cup doesn't work very well. The other one, the suction cups work great. How does a suction cup work? What holds things? Okay, here's an example of a suction cup. This is my version of the suction cup. Not as technical or pretty, but it works just fine. What is holding up this piece of metal? Okay, it's air pressure is the correct answer. Take it off like that, no problem. Try to pull it up like this. Of course, so you're my constant example. Try to pull it straight up. Can't do it, right? There's a lot of force holding that down. So what is making it work? Alex said air pressure. So let's just look at the suction cup for how it works. So we have there the sheet of metal, and on that sheet of metal, we have a piece of rubber. And let's approximate that that rubber is about 10 centimeters on a side. Now I take that sheet of rubber and I put on the metal, and what happens initially when I put the rubber on the metal? When I put it down, something happens with the air. What happens? Okay, air gets pushed out, just like when you clap your hands. You clap your hands, you hear a sound because the air is rapidly getting pushed out from between your hands. It pushes the air out. Now, you didn't do it fast enough to hear it, but the air gets pushed out. Then when you lift up, if you lift up on the center, that's supposed to be an up. If you lift up on the center, the rubber seals on the edges, and so you have virtually no air underneath and it's sealed. You pull up and that air underneath tries to expand. And while we haven't studied the ideal gas law or anything yet, you probably know that PV equals nRT is if the temperature stays the same and the volume increases, the pressure really drops. And your volume would increase by, order of 100, just raising that thing by a millimeter. So the volume goes way up, the pressure goes way down. For our purposes, we will approximate to say that the pressure between the plates, so now we're going to have an expanded view. Here's the plate, and here's our suction cup. And we're going to say the pressure in here is approximately 0. Is it really approximately 0? No. It's probably on the order of 100 pascals or more. But compared to atmospheric pressure, it's dropped a lot. And of course, on the bottom of the plate, we have pressure atmosphere. Now, normally with this plate, we have pressure atmosphere all over the bottom and all over the top. But now we're changing because we're reducing the pressure just in the area of the suction cup. So I'm only going to use the area of the suction cup for my calculational force on the top. I'll use the same area on top and bottom, and so my area is equal to 10 centimeters times 10 centimeters, which is 0.1 meter times 0.1 meter, hence 0.010 meters squared. That's the area. And so I'm going to use that area for both top and bottom. What is the force of atmosphere pushing up on the bottom if that's the area? What's the equation for force related to pressure?
Pressure times area.
Force is pressure times area. Okay, what about the force pushing down on the top? That's going to be force top is equal to pressure top times area, which is approximately 0, because we said the pressure top's approximately 0. And then, of course, we have to consider one more force. Force of gravity is equal to mg. If it's in equilibrium, if I say some of the forces in y, I have to define what direction y is. I have my upward force minus my downward forces. Okay, I put equal 0 twice, sue me. And so now I can solve this and say that the force of atmosphere is pressure atmosphere times A minus 0 times A. I'll put force top still. Factor out the A. And what we can do now is we can calculate what the maximum force that that thing could lift would be. The maximum force that it could lift would be the area, 0.010 meters squared, times 1.013 times 10 to the 5th pascals minus 0. And that's going to be 1 . 0.013 newtons. I could lift something that has a weight of 1,000 newtons with this suction cup if it seals perfectly. And if it's 10 centimeters on the side. I didn't measure it, so that's just an approximation. I think it's about right. So, of course, Corso couldn't pull it off. That's a huge amount of force. You tend to not think about how big the force is from gravity, or not gravity, from air pressure. But that's a huge air pressure force difference that holds them together. So, do you understand how a suction cup works? Now let's think about your practical application of suction cup before I move on. Practical application of suction cup. If you're going to stick a suction cup on the wall of your shower, what's the process you go through?
Make it wet.
Okay, make it wet first. Why would you make it wet first? The what? A better seal. If you really want your suction cup to stick, you want to clean the surface first, because if the surface has grime, it's going to make it so the surface is bumpy and doesn't seal as well. And then, yes, you make it wet, so when you stick it on there, it will stick better because it will seal better. The water helps you seal, then it dries. Final thing, the suction cups are not just a flat piece of rubber like this. We saw the flat piece of rubber works, but you also see that it comes off easily if you go off sideways. Why? Because I don't have it pulling out. So the suction cups you buy come with a shape that already looks like the picture that I drew. They come with a shape so that it's got a little cavity in the center. You push it all the way down to push out air. You let go, and the shape of it rebounds to make it so even when you just have it sitting there, the pressure underneath the suction cup is less than atmospheric pressure because you pushed out all the air and then expanded on its own. And so it sticks on there. If you pull on it, the pressure is going to drop even more because as it expands, the pressure drops and it holds even stronger. So that's the fundamentals of suction cups. We use them all the time. We tend to think they're magic. Now we know it's not magic of any way. It's just physics. Cool, right? I get all excited. I'm sorry. Surface tension. Picture from the textbook. Explain surface tension. When I was a child, we would go and spend a week every summer just outside Yosemite in a little town called Fish Camp, friend-owned property. And I love to look at the water striders on the water. You guys know what water striders are? Okay. Most people said yes, some said no. For those that don't know, water striders, we also call them skeeter eaters. I don't know if they actually eat mosquitoes or not, but they look like big mosquitoes. And they often land on water and they stand on the water. I believe mosquitoes can stand on the water too. And so that's what this picture is showing, is the foot of one of these water striders standing on the water. And of course, as a child, I'm like, how can it stand on the water? And you know me now. What do you suppose I did as a child? I tried to see what was going on. So I did things like push the water strider underwater, see if he can climb back out, trying to figure this out. No, we couldn't climb back out, by the way. Being scientifically inclined isn't always the most humane thing if you don't think it through. Well, what we understand from physics is that the water has what we call a surface tension. That surface tension is called surface tension because our calculations are going to be just like if it was tension in a string. The surface tension is caused by the water molecules having a certain cohesive force, a force making them want to hold on to other water molecules. So in order to separate the water, to break it apart, you have to exceed the force that's trying to hold them together. And so we call that force holding them together the surface tension. Another name for it is the surface area. That's why I put surface tension / surface area. And we calculate the force due to surface tension the same ways we would with the string. So if we look at this picture here of the needle, if this needle was being held up by a string, that is, if we had there's our needle, and we have a string that goes like this, we learned that the string makes a force on an object every location where it leaves the object. So how many places is there going to be a force of tension here? It leaves there and there, so I'd have a force tension here and a force tension there. And the angle, of course, is the angle at which it leaves. Now, if we talk about water, the water surface is not a one-dimensional, it's a two-dimensional thing. Of course, it's actually three-dimensional when it dips down, but a flat water surface is two-dimensional. And so if we put the skeeter eater's foot on the water, it looks very similar, except if you looked from the top down or the bottom up just on the contact, you'd have the contact is a circle with the water going up all around it. Okay, making it in red was not, with the water going up all around it, so the water's going like this. And so I would have a force going away from this foot in the direction of each one of those little black lines. And of course, it's actually continuous. So if we want to calculate the force, we need to calculate the force is equal to the force per length multiplied by the length of contact. So the force per length is the same idea as tension, except it's the tension per length of contact. And that's what we define as the surface tension. Oops. So I have on here gamma is the force over length. That's the surface tension. So if I look at the picture of the water strider, there is a certain value for the certain tension, for the surface tension of water. That surface tension depends on temperature, so you have to know the temperature of the water to do this calculation correctly. But I can say that the force net is equal to the surface tension times the length of contact. What was the geometry for that length of contact? I have my picture here. What shape was that red line for the contact? What shape is this? A circle. And so what's the length for the circle? It's what? It's the circumference. It's 2 pi times the radius. So for this situation, 2 pi times the radius is the length. But there's one more thing that I have to include. That one more thing is directionality. Because if you look at the arrows here, now it's only showing 2 arrows, one from the left side, one from the right side. But those arrows aren't vertical. So the force is pulling outward as well as upward. Well, the outward portions are going to add to 0. Otherwise, you got 1 foot and you go zipping sideways. That doesn't make sense. So the horizontal components add to 0. If I take this and break it into components, those 2 horizontal components have the same magnitude but opposite direction. But the vertical components sum together. And so I define this angle theta, and which part of my force of surface tension is the vertical part here, with theta divided as the angle from horizontal to where the surface tension force is pointing. It's actually opposite. And so which trigonometric function is that? So the net force on that foot is equal to gamma times 2 pi radius of the foot times sine of the angle. Now, if the skeeter is heavier, let's say the skeeter has just had a meal. Those guys are so light, it might double their weight when they have a meal. If you push down twice as far, what's going to happen to the skeeter? Okay? It might break the surface tension, but first it's going to sink down a little. As it sinks down, that water angle becomes more vertical, which means that theta is coming closer to 90, sine theta is coming closer to 1. So as it pushes down, the water angle goes more vertical until when you reach sine theta is 90 degrees, then you have the maximum upward force. You push down any more, it breaks the surface tension and it sinks. Once you break the surface tension, then it comes down to density if it's going to float or not. I saw a hand, but that was my angle of looking at one student's hand at his face and another student's shoulder. Just had to explain why I had that sudden lurch. So that's how a skeeter eater can stand on water. It's totally cool in my opinion. That's why a needle can float on water. Clearly a steel needle, a solid steel needle, should sink. And if you submerge it, it will sink. But it will float on the water. Now, many of you are thinking, how can I raise my grade? When I was in graduate school, true story I should not tell, I didn't study because that's what I did in college. And you know what happens when you don't study in graduate school? You do not thrive. So me and one other student both had GPAs of 2.67 after the first semester. And everyone with worse grades than us, they said, you've got to go home. Us, they said, you might consider leaving. And so I said, well, no, I'm not leaving. I'm going to try this new novel thing I heard about called studying. But my friend Steve said, no, I'm not leaving. I am going to enhance the efficiency of my mind. And so while I was spending my hours studying physics and got a 4 the next semester, Steve was staring at a needle floating in water, trying to change the orientation of the needle with his mind. After that semester, Steve was gone and I was still there. So just so you know, studying is a far more effective way of raising your GPA than trying to focus your mind on rotating a needle. Just had to point that out in case there was some cognitive dissonance. Here are values for the surface tension in different fluids. You look at mercury, that's a really high surface tension. Mercury has a pretty strong affinity to itself. Liquid gold, of course, gold is always your standard for almost anything. Very, very high. Water's a pretty low surface tension, but not low enough. When you wash your clothes, you want the water to get into small nooks and crannies. So what do you do to make so the water can get into the nooks and crannies? You add detergent. Now, soap and detergent are slightly different things, but basically what you're doing is lowering the surface tension. You guys have probably learned, detergent, you have one end is polar, one end is non-polar, and so the polar end will be attracted to water, the non-polar end will be attracted to grime, and it helps to latch onto that grime. But you also need to lower the surface tension. Something that lowers the surface tension we call a surfactant, a surface acting agent, surfactant. And the surfactant makes it so the water can get through into smaller regions. The surface tension is decreased. And so you look here, soapy water has a lower surface tension, almost cut in half. Depends on your temperature, of course. Brings up some interesting questions. We all like to blow bubbles, right? And to make a bubble, what do? Well, first you take your water and you blow. And what do you do with your water? You put in soap. Why do you put in the soap? I'll tell you what it certainly is not. You are not putting in the soap to make the bubble stronger, because the soap makes the bubble weaker. It makes the surface tension weaker, so it's not holding the water molecules together as much. As a kid, you probably can know by now, I said a little soap is good, a lot of soap is better. Not so. You put in a lot of soap, nothing works. Why do you put soap in the water if you want to make bubbles? If it's a surfactant, it weakens the bubble. Any ideas? I'm glad you had an idea, though. The answer is kind of surprising. Just like when I talked about, the detergent has the one polar end and one non-polar end. The soap does too. And so the polar ends of all of the soap molecules are touching water, and the non-polar ends will align away from the water, so you actually have a layer of soap on the surface of the water. And so that layer of soap doesn't evaporate, and hence your water doesn't evaporate. And so normally your bubbles pop very quickly because the water evaporates and you no longer have a bubble. But the soap keeps it from evaporating so you can have a lasting bubble. Because physics is really good to know for these kinds of things. I mean, what's a children's party if you can't explain to them all the intricacies of their soap bubbles? Now, here's another really important thing. Here. We like to breathe. It's considered a good thing. And how we breathe is often very confusing to people. When you breathe, you breathe. You've known how to breathe since before you knew how to do anything else. Right? Crying, breathing, pooping. Those are what you have going on when you're born. Well, if you think about how you breathe, to breathe in, you actually expand your chest. To breathe out, you contract your chest. When you expand your chest, you expand the gas in your lungs, which, according to ideal gas law, means that the pressure drops. And then the air pressure out here pushes air into you. So atmospheric pressure is pushing air into you because it's a higher pressure than the air pressure inside. If you look at consider parcels of air again, you have a higher pressure on one side and a lower pressure on the other. The parcel has a net force pushing it in. So you expand your lungs, pressure drops, air gets pushed in. Then to breathe out, you contract your little intercostal muscles here. You increase the pressure of the air inside. It's higher than atmospheric pressure, pushes out. That's how we breathe. If you were put into a situation where it's 100% atmosphere, but the atmospheric pressure is really low, you would still suffocate because you need the atmospheric pressure to push air into you. Right? You have to have that. One of the ways you can suffocate or you can die if you're shocked is if it's a shock that's across your chest and strong enough to cause your intercostal muscles to contract. It'll force you to breathe out and not allow you to breathe in. And so you could actually suffocate from a mild shock. That's why if there's some reason you have to test to see if a wire is hot, you never test it like this because it'll make your hand grab, and if it's going across your chest, it'll keep you from breathing. So there's one thing about how we breathe that has to do with pressure. Another thing is that we have surfactant in our lungs. Surfactant in our lungs to lower surface tension so we can have better flow in there. Now, am I a master of this whole thing? No. You can talk about it in your physiology class or biology, but there's surfactant there, so that's the first place most people hear surfactant. Talking about capillary action, oh, look, all my water has drained. That's why I put it in here today. This is not a great example of capillary action, mostly because I have virtually the same diameter in each one of these. This is a little smaller, this is a little bigger. If you look at the heights of the water, you can tell this one here is maybe 1 or 2 millimeters higher than this one, or you can tell if you get up close. So there's a very slight difference in the heights of the water. It's higher in the narrower one. Why would that be? Shall we talk about it? Okay, we'll talk about it. What's going on is we have a force of adhesion between the wall of the glass and the water. And just like the surface tension force, that force is in the direction that's pulling upward. So I'm going to call this force adhesion. And it's a force that's going around a circle, right? So I have the force adhesion. There's a certain force per length. And so the force adhesion is that force per length multiplied by the length, which again is a circle, 2 pi radius. And we have to consider the angle. So the upward force times sine of theta. Now, unlike with our skeeter, if you have a higher adhesive force than cohesive force, then it's going to work toward having a vertical angle, right, getting the maximum upward force. And so you're going to actually have sine theta is equal to 1 at the point of contact. And so this is going to be 1. So you have a net upward force of the force per length times 2 pi radius. Now, if we look at this column has a height of h and a radius of r. Then I'm going to have the force of gravity on this column. Force of gravity is equal to mg is equal to rho vg is equal to the density times pi r squared times h times g. So that's the downward force of gravity. I'm going to have an upward force due to atmospheric pressure. Now, is atmosphere touching the bottom of that column? No. But it's atmospheric pressure because over here, atmosphere is touching that height. And so staying at that height by Pascal's principle is the same pressure. And at the top, I have, again, force top equals pressure atmosphere times area. Using Newton's second law, sum of the forces in the vertical direction equals 0, which means that I'm going to have the force adhesion plus force atmosphere minus force top minus force of gravity is equal to 0. Now, we just saw the pressure at the top, the force top and the force atmosphere are the same, so those add to 0. And I end up with force of gravity is equal to force adhesion, which means that rho pi r squared hg is equal to 2 pi r times whatever that force adhesion per length parameter is. And it actually is just the surface tension. And so we can calculate the height here. I forgot something, didn't I? Oh, no, I didn't. So the height will be 2 pi r gamma over rho pi r squared g. Cancel one of the r's, cancel the pi's. And so you can see the height that the column will rise to depends on the radius. If you have a bigger radius, what does that do to the height that the column will rise to? It's lower, right. The density of the fluid, in this case water, and the surface tension. So that explains why we have capillary action. So our second clicker question, why is capillarity more obvious in a smaller tube? Do what? Oh, I forgot to think about that. I'll mention it in just a minute. I will try to move it. Okay, waiting on Eric and Brittany. Okay, we had 4, 7, 12, 0. Now we had a lot of variation on this. So we just went over and just had the answer. The answer is right there. Talk to your neighbor and see if they can help straighten you out on what the answer was. Okay, after you've discussed it, go ahead and answer the question a second time, and let's see if they move the right direction or the wrong direction. It accepted one person, and then it said, forget the rest of you. It liked that one person. Sorry. Okay, we won't do the repoll, and I will instead call on Ms. Aka, who you can tell is thrilled that she gets her chance to shine.
Okay, so I chose B, but when we discussed B, but C might be right.
Okay, so after you thought you chose B, but you thought B might be right. Or C, yes, C might be right. Now, the fact is neither of those are right. Well, no, that's okay. That's okay. I clearly wasn't correct or wasn't effective in explaining this because the correct answer was A. So let's come back to this. If we had a smaller radius, what did that do? It was A. A. Okay, so let's look at the force that's pulling up. What happens to the force that's pulling up as the radius changes? The force pulling up is this right here. As the radius increases, what happens to the force pulling up? It increases. So the upward force increases as the radius increases, which would tend to make you think, so it's going to have more capillarity with the bigger radius because the upward force is bigger. But if you look at the downward force, as radius increases, what happens to the downward force? It also increases, but it increases as radius squared. So the downward force increases as the square of the radius. The upward force increases proportional to the radius. Thus, the height, which is the result of having net force is 0, is proportional to 1 over the radius because the column's weight increased at a greater rate than the upward force did. So that's why the answer was the weight of the fluid in the tube. Oh, wait, that says it's, when it gets smaller, then the weight decreases. So that's why as R gets smaller, the weight in the tube gets smaller faster than the upward force due to capillarity decreases. Okay. Next, we were going to talk about flow rate. So I guess we won't talk about flow rate today. One thing that Corso wants to talk about is the exam that's scheduled for 1 week from yesterday. I do not feel ready to give you another exam yet because I've been going a little slow here. So I would like to have your permission to postpone the exam. If anyone is opposed to that, please contact me privately so nobody else says, ooh, I'm mad at person A because they're opposed to it. Right, so contact me before class on Friday if you're opposed, so I know. I would postpone to the following week, that's correct.